Once upon a time, the world was dark at night. Really dark. And the world was strange and changing and essentially ununderstandable or predictable. But there were the heavenly skies above. And since it was really dark at night, that was quite an impressive sight. A good 2,000 stars could be seen, and also a strange whitish trail, like a spill of milk. And there was no YouTube to spend your evenings, so plenty of time to lay on your back and watch the skies. And there was some nice, reassuring predictability there. Everything seemed to move in a regular and predictable way. The whole celestial sky with the stars rotated around a fixed point in the sky, returning every day at the same relative positions. Day in, day out, year in, year out. And not only the stars but also the sun, albeit with the seasons in a bit more complicated way. And then there was the moon, also predictable, with a monthly period and its phases from new moon to full moon to new moon and all over again. But there were some strange, not so predictable things happening. And the most spectacular example is a total solar eclipse. A scary, mystical phenomenon when the day turns into night in the middle of the day. A sign of doom and destruction. Lunar eclipses also occurred when the full moon became darkened. And then there were 5 strange wandering stars. Some of them were very bright and they didn't follow the same regular pattern as all the rest of the stars. Sometimes 2 or even more of them wandered very close. This picture of Jupiter and Venus I took myself, as you can see from the fact that it is not sharp. And by times, some even seem to move back against the background of the stars. And on top of all this, on rare occasions, a comet was seen, freaking everybody out. So, we have a more or less steady Earth, with mountains, rivers and oceans. And high above are the celestial stars, quiescently following the same pattern in a reassuring predictability. And between these two extremes is life, where all is dynamic with weather changes, seasons, plagues, wars, fights and everything growing and dying. And the wandering stars, the eclipses and an occasional comet with their unpredictability. No wonder people expected an influence of these ever-changing phenomena on what happens in every changing life. And I think it's fair to say that this is the basis of the firm belief in astrology that was generally held, also by scientists, including Kepler, until today. No longer by scientists though. Many cultures thought along these lines. The Western fascination for the heavenly skies can be traced back to Babylon in Mesopotamia around 1500 BC. Our existing signs of the zodiac were defined there, and it is also where the first documented observations of the positions of sun, moon and planets have been found. If you expect an influence on your life, on your kingdom, of the constellations of the planets between the stars, wouldn't you like to be able to predict them? Yes, of course. And that was, I believe, the driving force for a continuous effort over generations and cultures to try to accurately predict the positions of the planets and the timing of the eclipses. And that is a scientific undertaking. Positions are positions, irrespective of what significance an astrologer would see in it. To appreciate the breakthrough that Kepler accomplished, we need to understand the status of thinking and knowledge at the time that Kepler entered the stage in 1571. For that, let us go back in time to the Greek philosopher and mathematician Pythagoras, born in Samos 570 BC and died in Metaponto, Italy around 500 BC. He's well known for the Pythagoras theorem, though there is no historic evidence that he actually proved it. And Euclid was much earlier, including a proof. Anyway, but Pythagoras had many more inspiring thoughts. And most relevant for our theme is the almost mystical fascination of Pythagoras with geometries and numbers. And that was probably inspired by his investigations of music and harmonic tones. I don't know much about music theory, but this is how I would summarize. If you take a single string on a so-called monochord that Pythagoras used a lot, and you place a solid comb at a certain position in between, and you plug both sides, then only at very distinctive places of the comb that sounds nice. The ratio of the two lengths should be a regular fraction, like 1:2, or 2:3, or 3:4. And the fact that there is this strong relation between plain numbers and, say, the mental experience of music make Pythagoras attribute an enormous pervasive meaning to numbers. All is numbers, he said, not only on Earth but also in the celestial sky. And this idea will come back later in this series when we discuss Kepler. Another inspiring thought was his conviction that the Earth is a sphere. Pythagoras is believed to be one of the first philosophers that explicitly made that claim. 300 years later, Eratosthenes was able to estimate its diameter quite accurately, essentially by measuring length of shadows at different latitudes. There's a lot more to say about Pythagoras and the Pythagoreans, including around the question whether he really existed as a single individual at all. There's not a single document of him. He was a kind of a cult figure to whom all sorts of things may have been attributed by his later followers. But let's not go there. Fast forward to Plato, around 400 BC. Plato was strongly inspired by the Pythagorean ideas. This can, for example, be seen from the special role Plato attributed to the regular polyhedron. A regular polyhedron is a three-dimensional object consisting of identical regular polygons, such as a square, or a triangle, or a pentagon. It was already known that there could only exist 5 regular polyhedra of convex form. Euclid had already proven that, and Plato believed that all materials were made of elements with these shapes. And these 5 regular polyhedral structures are also referred to as the Platonic solids. Remember them, as they will make a glorious, though temporary, reoccurrence. Plato also had ideas about the heavenly skies. He saw a celestial sphere with the stars that revolved around the Earth in 24 hours. He was also aware of these strange bodies that did not move similarly: the Moon, the Sun, and the 5 visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. These latter strange wandering objects were called planets, after the Greek word for wanderer, planetes. But Plato believed that they too must move in perfect circles at uniform speed, carried around the Earth by gigantic transparent and weightless crystalline spheres. A bit like this, but then without this. He didn't worry too much about details that could spoil the model. The exact opposite of what Kepler would do 2 millennia later. Plato had a pupil, Aristotle, that would grow out to be a very, very influential philosopher. He lived from 384 to 322 BC. Funny how all these guys show up in marble. I wonder what Kepler would look like. Ah yes. Aristotle made a distinction between chaotic earth and the celestial skies. He also preached that all celestial bodies moved on perfect crystalline spheres with constant speeds. In fact, everything up there is total perfection. Funny enough, Aristotle also did not worry too much about the messy surface of the supposedly perfect above Earth body we call our moon, or the irregularity of the planetary movements. The Greek philosopher and mathematician Apollonius of Perga, living between 190 and 240 BC, reportedly did worry about them, particularly about the strange retrograde motion of the planets against the background of the stars that we mentioned earlier. He's believed to be the first to introduce epicycles to explain that strange behavior. But more on epicycles later. He also gave a proper mathematical definitions of conical sections, hyperbole, parabole, circle and the ellipse. Fast forward again. Now to Alexandria, to the Greek astronomer Claudius Ptolemy, who lived between about 100 and 170. He would become very influential with his model of the planetary system, where he did a serious but complicated attempt to describe the orbits, such that their future positions can be accurately predicted. He used his own as well as previously documented observations of the positions of the planets against the background of the stars. And this was all documented in his masterpiece known as the Almagest. His first step was to put the Earth in the center, as everybody had done. And all the heavenly bodies are orbiting the Earth in the order of Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturnus. This Aristotelian starting point was not able to explain retrograde motion. And in the Aristotelian spirit that everything that revolves sits on a circle and moves with uniform speed, Ptolemy called for epicycles. The planets were now moving on a relatively small circle, the epicycle, whose center was in turn moving on a larger circle, the deferent, around Earth. All at constant speed, of course. That is one thing explained. Another unexplained observation was that planets were changing apparent size and brightness. Even the moon. We know the highest brightness point of the moon is our supermoon. Ptolemy's solution put the Earth slightly off-center. Now the distance between planet and Earth changes, and that explains the changes in brightness. Yet there was another discrepancy that could not be described by the epicycles. The planets seemed to move at non-constant velocity over a year. Aristotle rules, so velocities must be constant. And that resolved with the complicated concept of equant. That is an imaginary point out of which the planet seemed to move at uniform speed. Such a concept looks overly artificial. but you can use it to make reasonably accurate predictions. If you think of it, it is pretty amazing that he could construct something that worked reasonably well, considering the fact that the real constellation of the planets was completely different, as we now know. The price to pay were the rather artificial concepts as the epicycle, he needed lots of them for small corrections, off-center Earth and particularly the equant. It's even worse because he used these three corrections inconsistently, one for one type of observation and another for another set of data points. If you can't follow, don't worry. We know better now for already 400 years. But the world had to wait another 1400 years for Kepler to radically doing away with them. After Ptolemy, not much changed about the vision of the universe in Europe. The Roman Empire came up, good for developments on judicial questions and engineering, but not for astronomy. The Catholic Church followed as a dominating power and the Bible as the book of truth. Only at the Renaissance, roughly 16th century, the interest in philosophy and astronomy grew again. By that time, many of the Greek sources had been lost, but fortunately the Arabs maintained an interest and kept the sources alive. A milestone is the publication of the Alphonsine Tables in 1483, sponsored by King Alfonso X of Castile in Spain. He had a team working on predictions of planet positions based on the full Ptolemaic system. Quite a job. And with that renewed interest, Aristotle and Plato re-emerged in European philosophy. But also the desire to predict the positions of the planets. Even more than that, fundamentally more, to explain them. And hopefully do away with the artificial and complicated construct of Ptolemy, with all respect. And the first critical step, or rather jump, was set by Nicolaus Copernicus in 1543. And in our next episode we will discuss the very important contributions to astronomy of Copernicus. His work was the stepping stone for Kepler to make his jump into modern science, half a century later. Stay tuned.